So good morning and good afternoon and evening from the various parts of the world. What I'm going to do is basically do a presentation on how we link the research we do to real end applications and how we see commercialization. But I'll start by explaining a little bit about what the Manufacturing Technology Centre does to provide you with context. Some of you may well have visited. I have hosted a number of visits from Indian delegations, industrial delegations over the years. So a bit of background to the MTC. This is the sort of MTC campus. It was opened in 2011 and I joined February 2012, but I was actually working from that Christmas of 2011 trying to build up the activity. It's an independent research technology organisation, and it was set up to bridge the valley of death, linking brilliant research undertaken by universities around the world and what industry needs. Industry wants really robust processes, what we refer to as high technology readiness level technology, not research that's still in the laboratory. And that's a missing link, not just in the UK, but in many countries. We need to prove innovative manufacturing ideas and also develop manufacturing system solutions. And that's the difference, though, is the all-encompassing system. And I'll talk a little bit about that later on. And very importantly, support industry with training. And we were established with 4 founding research partners: University of Birmingham, Loughborough University, the University of Nottingham, and also the Wells Institute. And it's a membership organisation. We have members from across different sectors, large companies like Rolls-Royce and Airbus, down to very small companies, micro SMEs, just starting their journey, commercial journey. Our primary markets are aerospace, defence and security, construction, space, transport, food and drink, healthcare, and utilities and oil and gas. Quite a diverse range of sectors, and it's interesting to see the dynamics between working in the aerospace sector compared to working in food and drink. Food and drink want developments in days, maximum weeks, and the aerospace sector has to take its time to ensure that it's got safe products that don't cause crashes on aircraft. And so there's a slight difference between different sectors. The Manufacturing Technology Centre is involved in a number of different manufacturing techniques, and they're grouped into 3 strands: component manufacturing, which is the area that I'm involved with, and that covers additive manufacturing, non-conventional machining, things like EDM and ECM, and also high integrity fabrication, a lot of it around welding. And then also assembly systems, so tooling and fixturing, electronics, robotics and autonomous systems, and then data. Data is really important, and that's around design and simulation, manufacturing informatics, which is critical now, drawing data from manufacturing processes to optimize their performance, and then also metrology and NDT. And interestingly, within the National Centre, we draw on all this capability. So although the additive manufacturing group itself is relatively small, it's only less than 100 people, it draws on world-class experts across all of these different groups to deliver projects which industry can rely upon. So for example, metrology and NDT is critical for our work in developing high performance AM components to ensure that they are have high integrity. So this is we're part of the high value manufacturing catapult, which was modeled on the Fraunhofer system in Germany. And there's a number of centres around the UK, and in fact additive manufacturing is represented in some way at many of these centres, right from the FRC in Scotland, Centre for Process Innovation in the northeast of England. We have the nuclear MRC and AMRC based in Rotherham in Sheffield. WMG, where I used to work years ago, at Warwick University, the National Competence Centre down in Bristol, and of course the Manufacturing Technology Centre in Coventry. And as Bhrigu has already mentioned in the opening, we're also the National Centre for Additive Manufacturing in the UK. So, in addition to that, we're also ESA's, European Space Agency's AM benchmarking centre since 2017. ESA recognised that additive is such a new technology that to try and generate a consistent approach to projects in AM, it needed one centre to ensure that, for example, feedstocks that go into the machines were treated in the same controlled manner. Otherwise, the research would be invalid. And we play a very important role in that, and our current contract has now been extended to 2022. And of course, we are a partner within a founding partner within the ASTM Centre of Excellence alongside. And there are more partners now. I have to apologise, but this has been a moving target. There's been more people recruited, and since this slide was generated. So what do we do? Well, we're the UK's independent AM body supporting the supply chain. So we're not doing research as you would see in a university. We're not. That's already been catered for. What we're interested in is taking new manufacturing techniques like AM into manufacturing, into companies making parts and making profits for industry. So, one of the things we can do, because we've been through this process with big companies, is to help companies follow that journey. Many companies are interested in additive manufacturing, but it's quite daunting. And we can say, look, we've had this experience. We can share this with you and say this is probably the approach for you that's worth taking. We can also help companies who are into additive already mature their processes and streamline their processes. And very importantly, help with workforce competency. Because one of the things we find is that if we have a new technology like additive manufacturing, the number of experts are very, very small. And that means that the skill level within industry is a shortage of skills, and we need to help bridge that. So we've got some excellent facilities, and for those that have visited, you'll know how well equipped we are, and we're always adding new technologies, new expertise. One of the disadvantages with AM is that every week a new machine is launched in the world, so no one can have every machine. There's not enough money and not enough space for any one centre to have all of the equipment. We do really well, but it is a challenge to keep on top of new technology, even for us, and that's important in helping industry. Another thing is to cover the whole process chain. So we tend to get focused on additive manufacturing as a process, but we need to consider things like design for AM, how we control the materials going into the machines, particularly because many of the machines, the materials have to be recycled to be used in the next process, and that control of the reuse is critical. Also, part setup and parameter selection makes a significant impact on the likelihood of a process finishing correctly and good parts being produced. And then there's all of the sort of processes after you've made the parts, heat treatment, the finishing, and very critically the part inspection. But I'll explain a little bit about that in a second. So say we've got some good facilities, we've got metals, lots of metals machines, both powdered bed machines, also adding now binder jetting technology, because we see that as a route through to higher volume production. and also large-scale directed energy, what is often referred to as WAM technology, wire and arc AM, and also laser DED facilities for making large components, measured in meters rather than millimeters. We also have an excellent polymers area, and I think as mentioned previously, polymers have taken a backseat a little bit in terms of end-use components. However, we're seeing now a strong pull from industry for high-performance polymers for some applications. So, and that's been a pretty interesting development over the last few years. And we're even seeing now ceramics coming through. And we have, in the UK, there's 2 ceramic production facilities for AM. So it's interesting that the ceramics, although still lagging behind polymers and metals, is a technology that needs to be watched carefully. So what is happening in AM? Well, for the last 30 years, the primary use of AM has been towards prototyping and research, but we are now genuinely moving from prototyping into production. And it's already been mentioned that some sectors have already spearheaded that development, particularly in the medical and dental sectors, where for some companies, additive manufacturing is the preferred choice. It is the way you make these parts. And that's really important because it shows also the way forwards for the next tier, the next round of companies who want to exploit AM. AM does bring significant opportunities, but it also has major risks associated with it. With a prototype part, and many of you on the call are using Objectify to make prototype parts and have been for several years. Once a prototype has been tested and used in its process, it then has no value and is forgotten about. However, with a production part, you own that production part. You have responsibility for that production part for the full life of whatever it goes into. So this may be a 10-year or even 20-year link between the part you've made and your customer. And that brings significant challenges. So I've listed some of the challenges. I don't want to put you off because I presume that most people on the call are avid AM users or certainly are interested in additive manufacturing. However, it would be fair to say that part cost, particularly for metal parts, is high. And that's linked to relatively low productivity levels, failed builds, and also scrap parts. But that situation is improving. New technology is coming through. We're already seeing that every 2 or 3 years, the cost of AM parts is dropping. And I think in the last 5 years, we've had a halving of the cost of metal AM parts as productivity is improved in the machines, and also the process becomes streamlined. And also failed builds are reducing because the machine's getting more reliable, and also because in-process monitoring has been placed inside the machines. They're no longer operating blind. And scrap parts are being reduced because we are starting to understand how to design for the process and set the process up correctly to limit the chance of failed builds. But however, there's still plenty of work to be done in improving the level of defective parts. Of course, it's a new technology, so there's lack of experience. So, you can't compare it with casting, where we have several thousand years of experience of casting. AM is new, and so we're still learning about the process, as one caller has mentioned. There's the fundamental science in some cases is still not understood. But we can't wait until everything is understood. We need to get going, and then as we move forwards and as the science helps us, we can then start to improve the processes and optimize the parameters. Another thing that some of you will have seen is the unconventional nature of part designs for AM. Design for AM, utilizing some packages, generates some fairly unusual component shapes. However, this is important. We have to break away from thinking about the sort of prismatic parts that we're used to as engineers, which have largely been dictated by previous conventional manufacturing processes, and let our imagination run, because some of these unconventional designs, although seem rather exotic, work really well, and they're highly optimized, and they also improve the build speed and cost of parts by reducing the amount of material that's being processed. There's obviously issues about materials. We don't have the wide range of materials we have for casting, but we are improving the number of materials. We need to control feedstock. This is really critical. We can't fill the machines with poor material and expect good parts out. And this is something that I guess most companies have to watch very carefully, particularly for metal AM. And we have unusual properties. What we're getting from AM parts is, in many cases, better than the casting, but we have to be careful because we do get anisotropic properties. We don't have consistent properties in all directions, and that has to be considered in the end-use application. And finally, we're dealing with really complex parts in the main. When we design them, we can integrate components, we can make complex components, but that makes them difficult to finish and difficult to inspect. And unless we can inspect a part, then we can't use it. So it is challenging. And as already mentioned, there's a lack of AM-specific standards and routes to certification, but these are now coming through. So particularly supported by activities like the ASTM AM Centre of Excellence. So as mentioned about controlling feedstock, many of the powder bed machines are using a fine metal powder. The powder itself will influence both the process and the component properties. There's batch-to-batch variation and supply-to-supply variability, which at the moment, although it has improved, it is still there, and it is a significant concern. And one of the things that the ASTM AM Centre of Excellence is working on is new standards for testing, which allow us to generate more confidence in the materials we're using. And of course, we need to know how much the AM process affects the powders, how it degrades the powder during the process. Can it be reused? One of the critical questions we get asked by industry is, how many times can I use the powder before I have to retire it? And that's really difficult because it depends on what you're making as well as the powder type. And things like, how do we store the powder? Does that affect the properties? What can go wrong? Can we get material, debris, with foreign object debris within the material, which then contaminates it and prevents it from being used? So it is, I would say, as part of the process, feedstock is one of the most challenging parts of the metal AM process and must not be overlooked. So within the ASTM AM Centre of Excellence, we've got a lot of work going on to support standards. We've got the projects funded by STM. We've also got core research projects funded by our members to develop new standards. So they're using their own money to develop standards for the greater good of the whole of the industrial sectors. We also have European projects, UK funded projects, the work we're doing with ESA, and existing standards activities. And one thing that's really important now is that when we run a research project to develop a new process or a new material, we're thinking about the standards whilst we're actually running those projects. The projects don't think about standards as a secondary issue, but are thinking about standards from the get-go. I want to mention a bit about how the research community can help. And one of the things that we need to do within the research community, as well as developing new processes, materials, and the underpinning science, is to help the technology move up the technology readiness level scale. So at the moment, if you look at the research area, generally speaking, we get to technology readiness level 3, and it's an experimental proof of concept. But industry can't use it until we get to 7, which is a proven process demonstrated in an operational environment. And that valley of death is that light blue area, which is not easy, it's not simple, and is quite a different approach to most university research. It's about refining and fixing parameters, and then validating the process and part performance, and then transferring that into industry, including training. So this is an important way the research community can help. Here's an example of that, where we worked with Royce. We did a project which was to develop a process for making these sector stator components here that are each individual electron beam melted and then welded together to form this ring of vanes. And the original process parameters were developed by Sheffield University, and then we continued to make parts, testing the robustness of the process for almost 2 years, making parts to understand how robust the process was before Rolls-Royce could use it in production. So one thing I would say is become an intelligent customer, keep informed. So today's session is really good. I really thank Objectify for setting up this webinar. We need to network and share information with other users. We need to participate in collaborative research programs to share the cost and reduce the risk. And also carefully plan your journey. Choose the right part. It has to be appropriate for AM. Otherwise, there's no point. You'll end up with a result that doesn't really work. And then take small steps to reduce the risk. Use an example from Boeing or GE, where they started with a small component, simple components, and then slowly built up experience and confidence. But also understand the bigger picture. You can only get the full benefits of AM by designing for the process. If you're using existing design, you will not be able to get the full commercial benefit. Here's some of the sectors that are using AM. I can quickly say that the usual ones we'd expect: aerospace, space, medical, power generation, motorsport and defence. And interestingly, in terms of applications, prototyping is by far the greatest application at the moment. But we shouldn't overlook things like manufacturing aids, things like jigs and fixtures and tooling. End components is still, in many sectors, some way off. And this is an example in jigs and fixtures. Many of the examples come from the automotive industry, where making jigs and fixtures, it's an expensive, tends to be an activity that is the last part of a process before you start production. So often it's under significant time pressure. And additive manufacturing offers a really good way of making complex fixtures, which are also lightweight as well, so making it less effort for operators to move them around a production facility. I'm getting to the end of the presentation. AM collaborative projects are really critical, and these are some examples of the ones that we're involved with. And I'll give you an example of just one project which shows you how we can take technology forwards for industry. This is the Drama project, and it's really about helping the aerospace supply chain exploit additive manufacturing. Big companies like Airbus and Rolls-Royce really don't need this support, but the smaller companies do require support, because for them the cost of getting it wrong is too great. So Drama has set up a UK facility and also tools to help UK supply chain gain a competitive advantage in the aerospace and additive manufacturing sector. And these are the project partners. We've got ourselves, ATS, who are involved in manufacturing systems, Autodesk, Granta, who you may know, who provide material property information, the Midlands Aerospace Alliance, Renishaw, who make AM machines, the National Physics Laboratory, who is a little bit like NIST in the USA. They have some great technology for measurement, and the University of Birmingham. And then we also have an industrial steering group who involves some of the bigger companies, because what we want is for those companies to buy into our solution. We've built a brand new facility that demonstrates the whole of the process, from design, powder testing and control, a range of different AM platforms, post-processing inspection, and it's effectively a reconfigurable factory. So companies can come in and test their product through this factory to see if it works. They don't have to buy any equipment, and so the risk is relatively low, and also they can use our expertise as well. And it helps them answer some of these critical questions. I think the first question is, do I need AM? Is AM really something important to me? And then probably, how do I get the method approved by my customers? Because if you can't get the method approved by your customers, you're wasting your time. And then think about what sort of capability, what sort of technology, and how should I lay out my factory? And this is something we can do through this facility. We also are taking knowledge that we're generating from the facility and sharing it across the world through our knowledge hub. So this contains this knowledge hub is contains information on the white papers on how to set up part builds, how to finish components, heat treatment, all sorts of technology, and it's free to access for companies. And finally, we need to bring it all together. This infographic is really to show what AM in industry should look like if it's brought together properly, starting with materials. How do we validate the material selection, supply, and how do we control all of the elements of powder handling and reuse? So all of those issues of material. And then, design for AM, choice of software, the knowledge of how to use it, optimizing the data flows and design to exploit that information effectively. And then information on the AM process, how to get optimized build strategies to give reliable builds. And then all of the work around post-processing to ensure that parts are fit for use. And then there's also issues around factory implementation. How do we design the factory for a smooth, streamlined flow of parts, and also health and safety as well? That's really critical. Some of these metal powders are both flammable and toxic to the users, so we're very careful how we deal with powders. And then also, how do we draw data from the machines so that we can continuously monitor, control, and also improve the processes? So I would say one takeaway is, have this as your aspiration. If you're going to get into AM, think about the whole system to maximize the benefit for your company, and of course work with partners, and also your customers, to ensure that what you're doing can be commercialized.